Okay, Trig class, we're going to expand today on the graphs of the first two trig functions that we did last time, which were the sine and cosine function. We are going to talk today about the tangent graph, and then we're going to proceed into the reciprocal functions, cotangent, cosecant, and secant. So we'll go ahead and get started. The first thing you should have here is your guided notes along with your handout. And here it's in color. Your handout was not in color. So you'll want to follow along with those as we go through. First thing we want to talk about is an asymptote. Now that's a concept you were probably briefly exposed to, maybe in Algebra 2, when talking about some graphs. If you look at your handout, you'll notice you have some dashed lines with the tangent and then with the reciprocal functions. Those are asymptotes. And what those are lines which a graph will approach. Okay. Approach, but will not intersect. So these graphs of these trig functions, the tangent and the reciprocal functions, will approach those lines, those asymptotes, but they will never cross them or touch them. So first let's talk about the graph of tangent. The graph of y equals, we're going to talk about the basic tangent graph, so the tangent of x. That most simple tangent graph is on your handout. As you look at that right over here, you'll see there's one part and then it starts down here at the bottom again and it would continue up there. So as you look at that, that graph actually repeats itself every pi units. So whereas our sine and cosine's period was 2 pi, tangent has a period of just pi. It is symmetric with respect to the origin, which hopefully you know that makes it a odd function. Remember, if it is symmetric with respect to the y-axis, it is an even function, and tangent would be an odd function in this case. Those vertical asymptotes, are located, remember they are vertical lines, so they are x equals some value. And what those will be for tangent is at 2 times k, where k is some integer, okay, any integer, plus 1 times pi over 2. And what that means, or what that is indicating there, is where k is an integer because tangent is undefined for odd multiples of pi over 2. So if you take a look at your graph, you'll see you have an asymptote here at negative pi over 2 and at positive pi over 2. So as you continue going, odd multiples, that would be pi over 2, it would be 3 pi over 2, 5 pi over 2, 7 pi over 2. That's what we mean by odd multiples of pi over 2. So that's where those asymptotes would be for tangent. Okay. Now the graph of cotangent is similar. Y equals cotangent of some value x. It is also on your handout. You'll notice this cotangent is right below it. There's a couple differences here. It's whereas tangent from left to right was increasing, cotangent from left to right is decreasing, right? It also seems to appear that the asymptotes are in a different location, right? So they're at here on the y-axis, they're here at pi, they're here at negative pi. So those are some differences between the tangent and its reciprocal function, cotangent. But what's not different is this graph is going to repeat every pi units as well. It's just that it has been shifted, right? That period, therefore, equals pi. This one is also symmetric with the origin, which makes it an odd function, like its reciprocal tangent. However, the vertical asymptotes are now at x, and the reason it's x equals is because they are vertical lines, right? If they were horizontal lines, they would be y equals something. X equals k times pi, where k is an integer, and that is because, if you look here, they occur at 0, at 1 pi, it will occur at 2 pi, 3 pi, 4 pi, 5 pi. So instead of every half pi, there's an asymptote, every pi, there's an asymptote. Okay? That's the difference between tangent and cotangent. Because cotangent is undefined for multiples of pi. And you can understand that as it relates to our unit circle. Remember that tangent is undefined because you end up with 0 in a denominator at 90 degrees, which is pi over 2, and at 270 degrees, which would be 3 pi over 2. However, cotangent would put a 0 in the denominator at pi, which is 180, and at 0 or 360, which would be either 0 or 2 pi. So that's kind of the relationship there as these graphs relate to the unit circle. Okay. Now let's talk about the other reciprocal functions, the reciprocal of cosine and the reciprocal of sine here. They will be related in their vertical stretching, their period, their horizontal stretching. Everything that applies to their reciprocal function will apply to these. It's just that since these are reciprocals, they will actually, you'll see from the graphs, they'll be going in the opposite direction as their counterpart, sine or cosine, goes. So let's look first at the graph of secant. So y equals the secant of x, and that's also on the handout. If you look here, secant is below its reciprocal function, which is cosine, and you'll see it has it kind of has the same point here. It shares this point. However, secant goes in an opposite direction. And if you remember, cosecant and secant have some places on the unit circle or places on the coordinate plane where it is undefined. Well, they have asymptotes here. Okay? So wherever cosine equals 0, right here and right here, remember when you flip that over, 0 would be in the denominator, therefore the secant has asymptotes there because it is undefined. Alright, let's look here. As you could tell, the secant does appear to repeat itself every 2 pi, just like its reciprocal function did. So it repeats itself every 2 pi units, making the period 2 pi. It is symmetric with respect to the y-axis, therefore it is even, right? And these vertical asymptotes, as I indicated there when we were looking at the graph, wherever it's reciprocal, wherever it crosses the x-axis or that value is 0, well, when we take the reciprocal of that, 0 would be in the denominator, so I'm going to have vertical asymptotes again at multiples of 1/2 pi. So it's going to have vertical asymptotes at x equals, again it's going to be the same as it was for tangent, 2k plus 1 times pi over 2, where k is an integer, okay, and secant will be undefined, okay, so that's an integer. And the secant will be undefined for odd multiples of 1/2 pi, meaning 1/2 pi, 3/2 pi, 5/2 pi, 7/2 pi, all of the odd multiples there. Okay, the graph of cosecant is going to be the reciprocal of sine. Therefore, when sine reaches its maximum here, cosecant is at its minimum, and it, instead of going up then down, it goes down to that point and then up. Okay, so you can really, and I'll illustrate this in our example. I think sometimes it's easier to graph the sine or cosine and then graph its reciprocal function, because you can think about some key spots on the sine and cosine graph. Whoops, wrong one. So this graph of cosecant, write this out, y equals cosecant of some value x. It's on the handout, we looked at it. It also repeats every 2 pi units, indicating that the period is, for this particular one, is 2 pi. It is symmetric with respect to the origin, just like its reciprocal function was. So therefore it is odd. Okay. The vertical asymptotes are at x equals k times pi, just like cotangent was, where k is an integer. And that is because cosecant is undefined for the multiples of pi. So pi, 2 pi, 3 pi, 4 pi, 5 pi. Okay. Now, again, these were the basic functions, just like y equals sine x, y equals cosine x, and as you recall from the previous lesson, remember that we added things to it. We added some c value, which produced a vertical shift, and that either moved up or down, remember, depending whether c was positive or negative. A produced a vertical stretching or shrinking, and what that will do is that will take this value, so either this local minimum or this local maximum, and move it up or down according to what the a value is in the equation. And remember that B produced a horizontal stretch or shrink. Okay, so what that will do is just stretch out the period, right? Stretch or shrink. So you'll have the same graph, only it will be shrunk into a smaller space or stretched out into a larger space. Okay. Just want to remind you that B does not equal the period, right? Rather, it's a component of the equation for period. And remember that equation for period It's going to be different now for because it is dependent on what the normal period of that graph is. So the period will equal 2 pi over b, and that will be for all of the graphs, all of the trig functions whose regular period is 2 pi. So that would be sine, cosine, and their reciprocal functions, which would be, whoops, I like to write them in order since cosecant is the reciprocal of sine and secant is the reciprocal of cosine. Now, the period will equal pi over b for tangent and cotangent, because those were the two functions who had a normal period of pi. Remember, that's the span with where it repeats itself. So, okay. We're going to go do a couple examples. Again, I would encourage you to do these and check these on the calculator. You need to be able to come up with the key points on the graph, but it's a good idea to check these with your calculator so you know you're doing them correctly. Okay, we'll take a look at these all together. Alright, I want to graph two periods of the function y equals 1 plus 3 tangent of 2x. So as you can tell, I've got a c value, I've got an a value, and I've got a b value. So this is not going to be exactly like this tangent curve right here. The curve will be the same, but my values will be different. My the period, the key points where this thing changes. So let's take a look at this. We'll walk through it. So let's identify some things. C, whoops, let's go blue here. C is equal to 1, right? So what that tells me is that is a vertical shift up by 1 unit. So we will shift our basic graph up 1 unit. Okay. A is 3. So what that means is that will be a vertical stretch. And if B equals 2, then what that's going to tell me is the period. So my period, remember, for tangent is found by taking pi over b. So my period for this one is going to be pi over 2. So now I'm going to go label some key points. The first thing I like to do is show my center of the graph. So for the typical one, it is at 0, right? Well, I had a vertical shift. I shifted the whole thing up 1, so now my center is going to be right here. And sometimes it's a lot easier to draw the graph before you label, and then you can label things afterwards. It's completely up to you, but some people find that easier. So remember, there's always a key point a quarter of the way and then at the end of a period. So at the quarter, what I'm going to do is I'm going to imagine that there are asymptotes in right here at the second spot and over here, right here. Okay. I had a vertical stretch of 3. Well, what that means, if you'll notice here on the regular graph, there's a point of reflection. Okay, so this is kind of curving out, so it's open up into here. But then at this point in time, well, there's no reflection here. The reflection is right here, right? But at this point in time, halfway through, okay, is kind of where I want to show it, because it will be halfway to the asymptote at this, what we typically refer to as the amplitude, right? Because our basic amplitude is 1. Well, when we have a 3 in there, when we have a 3 for that A, that point halfway to the asymptote is going to be 3 above the center. So 1, 2, 3. So I'm going to have a point right there. Okay, and I'm going to have a point halfway to the other asymptote, 1, 2, 3 below that. Does that make sense, hopefully? And then this point in our center is our point of reflection. So let's go in and add our asymptotes here real quick. Let's make those red. So, oop, it's too far over. Okay, that's going to be our asymptote there. It's our asymptote there. So if I went, that's 1, 2, 3, 4 spots. So 1, 2, 3, 4. Yeah, undo that. About right there would be our other asymptote, right? Because we wanted to graph 2 periods here. So go back to my pen, and I'll just do my best in trying to draw this in. It's kind of hard on this. Whoops. I'm going to start over there. So I'm getting real close to that asymptote. I know I'll never cross it, right? So that's really stretched out, isn't it? Okay. And then I can just kind of pick that up and transfer it all over here, right? I've got a spot right there. I've got a spot right there. I've got a spot over here. Remember, it's just like we pick that up and move it. Okay, so I'm going to draw that in. Okay, not bad for freehand right there. Now I need to make sure that I label everything appropriately. So this was 1, 2, 3, 4, and that would make sense because that should be 3 spots above my center, right? -1, -2, that would be 3 spots below. But then I need to label my horizontal as well. If my period is pi over 2, then I know that this whole thing between here needed to be half pi. So if I've got a half pi over here, or if I've got half of that over here and half of that over here, that means I need a quarter pi and -1/4 pi, right? So then this center right here would be another quarter pi, so that would be half pi. And then this would be another quarter pi, so 3/4 pi. A quarter, half, 3/4 of a pi. Okay. And that's how you would graph the tangent by hand. Remember, you'll always want to check that on a calculator, and we'll go over all that in class. Okay. Now I want to graph 2 periods for the function y equals 2 times secant x. First things to identify: c value. I'm not adding or subtracting anything to it, right? So c is 0. I have not shifted. Okay, so there is no vertical shift. Okay, A is 2, so that is a vertical stretch b is 1, right? There's an imaginary 1 right here in front of the x, which means that the period would be what it normally is for secant, which is 2 pi. And if I didn't recognize that, 2 pi over b, 2 pi over 1 is 2 pi. So that means that this graph is going to repeat itself every 2 pi units. Okay? Now, I think that sometimes it is easier to go in and graph the reciprocal function, because those seem to be the one that people catch on to. So the reciprocal function would be y equals 2, and what's the reciprocal of secant? It would be cosine of x. So if I were to graph that, I know the amplitude is 2, right? So I know I would have a spot. Cosine starts at the maximum and goes down, and it crosses, remember, right there, and then it would get to its minimum, and then it crosses again, and then it gets back up to its maximum. Okay? So if I'm drawing that over here, and you'll have had plenty of practice on this in class on Monday or Tuesday, whenever you have me. Okay, so that's starting to look like that curve that we want. I'm going to freehand this to the best of my ability. Let's see here. Not bad. Not bad, not bad. Okay. So, the reason I think that it is easier to draw that is because that's pretty straightforward. I can, once we've got a little practice, we can draw that in pretty easily. But what I can also identify here are the asymptotes, because where the reciprocal function, so where cosine is at 0, that's where my asymptotes are going to be for secant, right? And I can also label at this point in time. Okay, so if I'm labeling, I know that this is 2 and this is -2, right? I also know that I didn't affect the period, so I went through one period. This must be 2 pi out here, which would make this in the middle be pi, and these others would be at the half pi and 3/2 pi, so on and so forth. So -pi, -2 pi. Okay? So I've got all those key points labeled there. So now all I have to do really is think about where are my asymptotes. Okay? So let's go in and draw in the asymptotes. Well, they're going to be where cosine crosses 0. Whoops. So there's an asymptote. There's an asymptote. It crosses 0 there as well. And right there also, right? So then I think about my actual graph of the one I want to get to for secant. Make sure I'm going solid here. And remember, it goes in the opposite direction as its reciprocal function. So if I start here, this went down, so it should go up. This went down, so it should go up. So my graph of secant should look like this. And where this was going down to a minimum, I kind of have a maximum in here, right? Meets up there. Not bad. If I wanted to go ahead and complete this, this one would be another one like this. A lot of times it will be shown with just that half of it, because we could continue it over there, right? just be shown approaching that asymptote. Okay, so that would be a full 2 periods. So here would be a whole period, here would be a whole period of y equals 2 secant x. If it helps you to go ahead and continue out there and finish those pieces of the graph, that's fine. Alright, we'll work on another Inspire activity, and then we'll look at 1 through 16 all on page 632, and then 9 through 18 on page 633. Thanks for following along. We will see you in class.